This is a lecture about neighborhoods and open, closed, and bounded sets in multidimensional spaces. When we talk about functions of several variables and the regions in which they're defined, these multidimensional spaces, then these terms, interval, open, closed, endpoint, limits, continuous, and differentiable, all these terms have to be redefined. We start by replacing the word interval with a more general term, region. And now we have to determine if the region is open or closed or neither, and that requires definitions for some new terms. One is neighborhood, and the others are the interior and boundary points. A neighborhood about some point in Rn is a connected region that has the same dimensions as the space. That means if you're in R2, it has to be a two-dimensional figure. If you're in R3, it has to be three-dimensional. And this neighborhood also must, of course, contain the point that you're talking about. And I'm going to denote the point as x naught. Let me find the pin. Let me find the right end of the pin. So x naught, y naught is going to be the point we're talking about if we're in R2. If we're in R3, it will be x naught, y naught, z naught, and so on, depending on the dimension of the space that you're working in. So it has to contain the point. It has to have the same dimension as the space. Connected refers to a property of a region. For example, if I had something like this and said this was my region, it's not connected because I can't take a point here and draw any kind of line between them and stay completely in the region. If I have something like this, it's connected. I could go from here to here by staying inside the region. So this is a connected region. This is not connected. So the neighborhood has to be a connected region, same dimension as the space, and contain the point. A neighborhood really could have any shape, but it's most convenient to use the unit disk if you're in 2 space or the unit ball in 3 space. And here is a definition for the unit disk. So it would contain the point x naught, y naught, so it's a disk about the point x naught, y naught. And remember, unit and unity in math refer to the number 1, so it will be some region that has some important definition of 1. In this case, it will have a radius of 1. The second expression is for, this one is for the unit ball. This is in 3 space. You have your point x naught, y naught, z naught, and you have a ball about that point. Often we just say a sphere, but a sphere actually is the outer hull of the ball. In one dimension, this would be R1, and here's your point, say x naught, then the neighborhood is just an interval about x naught. It doesn't necessarily have to be open. Neighborhoods are used to define interior points. We're going to have some kind of region shown here as labeled V. I usually label it S, but you have this region and it consists of many points. If you have, I'm going to take some point P, and if you can make a neighborhood about P such that that entire neighborhood lies inside the space, then P is an interior point. And that's what's shown here. The darker green is the neighborhood about P, and it's lying totally in the space V. How you typically do this is you take your unit disk or unit ball, and then you multiply it by some scaling factor to shrink it. And you shrink it down, and if in shrinking it, say this was your unit disk, this has a radius of 1. But as you multiply it by epsilon, epsilon being less than 1, you start shrinking that unit disk down, and if you can shrink it, like right there, so that it lies entirely within the space V, then P is an interior point of V. And that's written here, sort of set notation. Epsilon is the scaling factor, n is the unit disk, so here's my neighborhood. The neighborhood multiplied by epsilon, so it's scaled down, lies entirely this inside of the region S. Now we use neighborhoods again to define boundary point. if the neighborhood about the point P can never be shrunk enough so that it lies totally inside V, then P is a boundary point. What you're seeing here is a neighborhood about that point P of the region V, and it's containing points out here that are not within V. No matter how much you shrink this disk, it will never lie totally within V, so P is a boundary point. And that's what's expressed here. Epsilon's a scaling factor, N was the neighborhood you were, say your unit neighborhood, and it is not contained in S for any epsilon. So that's a boundary point. A region that contains only interior points is an open region, and the region is closed if it contains all of its boundary points. In many cases, the idea of interior and boundary points is intuitively obvious, but there are many examples that are non-intuitive. These are not necessarily pathological cases. They're in fact very common. The example I'm going to give is that of an interval. Here's this interval, let's say 2, 3, and let's look at it first in R1. So here's my one-dimensional space. Here's 0, here's 2, 3, and this is an open interval. Doesn't contain its endpoints. Looks like that. Okay. The neighborhoods in R1 are intervals themselves because they have to lie inside the region, and so for this point here would be a neighborhood about this point here. Let's say that point is 2.3. You see, you could find a neighborhood, find an interval about any point on this in this line segment, and that interval would totally lie within the line segment. Therefore, this is an open region in R1. Now let's look at the same interval, 2, 3, and look at it in R2. In R2, the neighborhoods have to be two-dimensional figures, so I'm drawing them as disks, circles. Okay. Now, any point that I pick between 2 and 3, and I want to construct a neighborhood about it, it will have to be a disk, such as shown here. That disk will contain points in the region, that will be those right along the line, but it contains many points that are not in the interval, because it's a disk instead of a line. Every single point will have this situation, so all the points are boundary points in R2. So this line segment is closed in R2. So it was open in R1 but closed in R2. Of course, it's closed in any space, any R to the n where n is greater than 1. If you put it in three-dimensional space, it would also be closed. We have an additional concept called bounded. The region is bounded if it can be contained in a disk or a ball of finite radius. Otherwise, it's unbounded. It might seem that closed and bounded are the same thing. If the region's closed, it should be bounded. This is not necessarily true in multidimensional spaces. The reason it might seem strange is because we developed intuition on the words closed and bounded when we were working in one-dimensional space, but that intuition doesn't hold in multidimensional spaces. If you looked at this line, R to the n, if you looked at any line, not just a segment, but the complete line in R to the n when n was greater than 1, you looked at the line in 2 space or 3 space or a higher dimensional space, just like that line segment, it would be closed because every one of its points would be boundary points, and it would of course contain all of its boundary points, so it would be closed, but it wouldn't be bounded because the line is extending, of course, towards plus and minus infinity. Another two terms that are not mutually exclusive are the terms open and closed. You might think if the region's open, it cannot be closed, or if it's closed, it cannot be open, but this is not necessarily the case. You won't have to describe any of these sets in this class. Sets that are both open and closed are the entire space and the empty set. These are very interesting concepts, this idea of open and closed intervals, or open and closed regions, and neighborhoods, and whether the region is bounded. These are all part of the study of topology, although you will see these ideas over and over again in analysis.